Ooh, there's a bug here. It's like a ladybug or something. You just launched it over there.
Oh, great stuff.
Yep.
It definitely was one of the. It wasn't a big deal, but it was one of the at least fun parts about math classes was especially your math professors.
Yep.
And you'd ask them, so how's this apply?
Yeah. Yeah. No, I mean that's part of the reason why we have this class is to kind of go over this stuff. I mean, you guys have seen all this stuff before. It's
Yeah.
just not the application.
The application, I think having a starting point, having a goal or a destination, it makes it easier to kind of connect the road.
For sure.
Versus in the math class, when you have just these are the steps you have to do, you don't really know why you're doing the steps, and then hard to remember the steps versus this, like, oh no, I know what I'm looking for.
Exactly. Exactly. Yeah. Yeah. Honestly, a lot of this stuff didn't click until like much later for me too, to actually see how it's actually used. So yeah, for sure.
You said projections is going to be more fluids based.
Yes. Yeah. You'll see a little bit today too. So actually, we're going to use the idea of projection so we find the directional derivative.
Okay.
Yeah. Yeah, projections is used a lot. I mean, I know the fluids application just because that's my own work, that's my own research, but yeah, it's used a lot. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there? I know it's the day before the midterm, which I know is I think everyone's pretty tired. But okay. All right, so plan for today is we're gonna be going over our calculus, basic calculus 3 stuff. So we did a review last time of just very basic vector algebra, dot products, cross products, vector addition, scalar multiplication, things like that. So today we're actually going to get into the calculus stuff. So we'll be going over 3 main operators today. So we're going over gradient, divergence, and curl. So hopefully those are familiar names to you guys. I hope you've seen them before. But I think the difference today is that, we'll actually look and see what some of these operators are used for, as opposed to, proofs of their properties. So hopefully that'll be exciting. One thing I literally just realized as I started talking today is that I forgot to post the solution for homework 3. I meant to do that this morning. So I will do that this evening as soon as I get back to my office. I haven't had a chance to grade your homework 3s yet, just because it's just kind of been a busy week for me. But I plan to grade them tomorrow. But I do want to get the solutions up tonight so you can use that to study. So I apologize for that. I meant to do that today, but I forgot until okay. All right, and so of course, our next class session is the midterm exam. So please make sure that you guys are all here for that. It is a 75-minute exam, so you want to make use of every second that you have. So please make sure to come to the class. If you can come to class a little bit early, that definitely helps too. Usually what I do for the exam days is I'll pass out the exam maybe like 2 or 3 minutes before. And if everyone's all settled, and I let you guys start a little bit early just to give you guys a bit more time. So coming early, getting a seat, I think is helpful, right? And just a reminder, the things you can bring for the exam, you can bring your writing utensil. Please bring a calculator, and you can bring 1 sheet of notes. And so one 8.5 by 11 sheet. You can make use of both sides, write it, type it, whatever you. Okay. All right, any questions I can answer before we get started regarding the content of the class or regarding the midterm exam? Okay, all right, so let's go ahead and get started. Okay, so last time we started our discussion with this idea of a field, right? Where, we essentially said a field is kind of really nothing more than just a multivariable function. That's its I would say that's kind of its strict mathematical definition. But the way we use fields in engineering analysis is that we usually use it to represent some kind of physical quantity that has its value changed in space. Okay. And so by space, I usually mean some Cartesian coordinates, right? So X, Y, and sometimes Z. Although we're not going to do too much in 3D because that just ends up being more computations. Okay. So for the most part, we're going to be looking at 2-dimensional situations, right? Right. So one that I'll kind of refer to a lot today, just because it kind of lends itself really well to this kind of theory, is this idea of the temperature field. Right. So the temperature field, whenever you have a thermal situation where you're measuring temperature as a function of space, right, we can say the temperature is a multivariable function that depends on X and Y. Okay. All right. So last time, we reviewed kind of just very basic things that you can do with multivariable functions that you can do with vectors. Today, we're going to start to talk about what I call differential calculus. Okay. So the term differential there refers to derivatives. Okay, so we're essentially going to be looking at derivative operations involving multivariable functions. Okay, now this is going to be a very much a crash course. I think, traditionally when you learn this in your math course, you spend, maybe weeks at a time learning some of these concepts. And so we're going to be spending one lecture. And so, we're going to be reviewing kind of what these operations do. But I think more importantly, we're going to talk more about how these are actually applied in kind of real life computations and real life applications. Okay. So the first concept that we'll go over is the idea of a partial derivative. Okay. So when you have a function of multiple variables, you can take derivatives of that function with respect to any of the variables involved in that function. Okay. So for instance, if you have a temperature field T of X and Y, okay? So we know that this temperature field is dependent on two spatial variables, X and Y. We can take its derivative with respect to X, and we can take its derivative with respect to Y. And those represent our two partial derivatives. So we have partial T, partial X, and then partial T, partial Y, okay? Right, because typically, when you take a derivative operation, you can only take a derivative with respect to one variable at a time. And so when you take a derivative of a multivariable function, we call those partial derivatives. Okay. Okay, and then of course, you can continue along as well. So you can take another derivative, right? Right. You can even take the cross derivative if you really want. And so you can take partial square T, partial X, partial Y. Although surprisingly, there's not too many applications for a cross derivative. Most of the time, we're just taking derivatives of just one variable at a time. Okay. Okay. All right. And so, when you take the partial derivative with respect to one variable, the way that you kind of mechanically do that is you assume all other variables that you are not taking the derivative of are constants. Okay. Because you're not taking the derivative with respect to those other variables. Okay, so even though they are other variables, the field does depend on them. When you do the partial derivative, you assume those other variables just behave as constant. So they're either, if they're, they may either go away or they just kind of just ride along for the ride. Okay, so very, very quick example, right? So let's say we have a temperature field T of X and Y is equal to 3x squared Y minus 7y to the fourth power. Okay. Right. So if we take the partial derivative of this function, so we'll take partial T, partial X, okay? We're only going to take the derivative of the X portion. So everything, so Y here is just going to be treated as if it were a constant, right? So we take the derivative of the first term in this expression, 3x squared Y. The Y is just a constant, so we just kind of bring it along. So we end up with 6xy. Okay. And then the second term in the expression, minus 7y to the fourth, there's no x here. And so, when we take the derivative of that, we end up with 0, because that portion of our field does not depend on x. And so the partial derivative with respect to x of this is just 6xy. Okay. We can also take the partial derivative with respect to y. Okay. Let's do that. We take the derivative of the first term. The x squared there now behaves as a constant. So we end up with 3x squared minus the derivative of the second term with respect to y. Now we are going to take the derivative of this because it does depend on y. So minus 28 y cubed. Okay, so very simple, right? So, hopefully that was kind of review for everybody. All right, another thing that we can do is that we can also take partial derivatives of vector fields as well. Okay. So remember, we talked about last time what a vector field is. So a vector field is basically a vector, valued quantity. So it has several components in the different directions, right? So when you take a partial derivative of a vector field, you're going to take that partial derivative of every component of that vector field. Okay. All right, so let's say that we have some velocity field as a function of x and y, right? So that means we have an x component of that velocity and a y component of that velocity, okay? Where each of the components of that velocity field also depend on x and y, okay? If we take the partial derivative of that vector field, we take partial v, partial x, okay? We're going to apply that partial derivative to every component of the vector field. So we're going to have partial u, partial x, okay, and partial v, partial x. Okay, so that was just a crash course in how partial derivatives work. Any questions on this? Okay, all right, so let's get to some of the interesting stuff then. So let's go over gradients first. Okay, so the gradient is a derivative operation that kind of plays off this idea of the partial derivatives. Okay, so when you take the gradient of a function, we're essentially interested in the partial derivative of every single possible variable in that multivariable function. Okay. Okay. All right. So gradient. We'll do the simplest one first. So let's take the gradient of a scalar field. Okay. Bless you. Okay, so the gradient of a scalar field will compute the partial derivatives in every single direction. Right, so the fact that we have a field tells us that we have a multivariable function, so there are going to be multiple independent variables here. Okay, so when you take the gradient, you're going to compute the partial derivatives in each direction, and then store the result as a vector. Or I guess specifically, it stores the result as a vector field. Okay, so mathematically, it looks something like this. So let's say that we have some function, and just for the sake of argument here, we'll look at a three-dimensional function. Okay. So let's say we have some function as a function of x, y, and z. Okay, so we have a three-dimensional field variable here. So if we take the gradient of f, and the gradient of f is denoted by this kind of upside-down pyramid thing. And if you're ever curious what this symbol is, this is called a nabla.
No.
nabla. Yeah. Or at least when you're using equation editor in Microsoft Word, that's how you get it. You do \nabla. Right? Okay, so if you take the gradient of f, this is equal to, right? So this is now going to turn it into a vector field, right? So our scalar field f is going to turn into a vector field when we take its gradient, where each component of that vector field is the partial derivative of f in each of the different directions. Okay? So we're going to have partial f, partial x, comma, partial f, partial y, and then partial f, partial z. And of course, if you only have if you only have a two-dimensional field, then your gradient will also only be a 2D vector field. Okay. Okay. So if we look at the example that we just did, so we look at our temperature field up here, we can form the gradient based on these results. Okay. So I'm going to look at just at that temperature field that we just computed. Okay. So the gradient of T is equal to, okay. First component, we're going to have partial T, partial X. So we computed that already. Partial T, partial X is 6xy. Okay. And then partial T, partial Y is going to be 3x squared minus 28y cubed. Okay. So this right here is the gradient of this temperature field. So T of xy is equal to 3x squared y minus 7y to the fourth. Okay. All right. So computing gradient is fairly straightforward. So as long as you can take a partial derivative, then it's good. Okay. Now, we're not going to spend too much time on computing gradients just because that's fairly straightforward and you've done that before. What I want to focus on more is, how do we actually use the gradient? So the gradient has a lot of really interesting uses that we can apply to do some very interesting types of analysis. Okay. Okay. All right, so the first application that we'll go over is this idea of the directional derivative. Okay. And this actually kind of builds off our discussion from Tuesday when we talked about the idea of projections, right? So remember when we talked about dot products, one way we can use the dot product is to project one vector onto another. And so you actually see kind of that application cube as well. Okay. Okay. All right, so what's the idea of a directional derivative? So oftentimes when you have a field quantity, you are interested in the rate of change of that quantity, depending on if you go in a certain direction. Right. So for example, let's say you have our temperature field there, right? So as we kind of have displayed up here. So you want to find out what's the rate of change of this field if you travel in the x direction, right? So, I always think of fields as kind of like a map, right? So think of the field as like a map and you're kind of standing on the map. And if you walk in a particular direction on the map, you want to see how, what change in temperature are you going to experience, okay? All right, so here is our domain here. So we have a two-dimensional field here. All right. On this field, we have our function t of x and y. Right, so based on that function there, we're going to have different regions of this domain here have hot temperatures, different regions of this plot here have cool temperatures, right? So we want to see, if we started at some location here, and we walked in this direction, right? What rate of change, or how is the temperature going to change as we walk from one location to the other? Okay. Now, that question by itself is actually quite easy to answer, right? Because we're walking in a perfectly horizontal line. And so if we want to compute the rate of change of t as we walk in the horizontal direction, there's an answer for this, right? Which is partial t partial x. Okay. So we have a partial derivative that accounts for that rate of change as we go in that x direction. Okay? That's exactly what the partial derivative tells us. Right? Same thing for the vertical direction, right? So let's say we want to walk upwards, right? And we want to find the rate of change as of temperature as we go upwards, right? We have a variable for that as well, which is partial t partial y. Okay. All right, so that's all well and good, right? And so, our partial derivatives there are aligned with our Cartesian direction. So, we can find the rate of change individually in each of those directions. Okay. Okay. But what if we wanted to find the rate of change in some oblique direction? Right? So what if we wanted to change, what if we were walking from here to here, okay, in that direction? How do we find the rate of change for that? I'll give you another example that I think is, maybe not strictly engineering related, but, it is related if you do any hiking, right? So oftentimes, if you're hiking in an area with any kind of elevation change, right, you can look up, or there are maps for this too. You can get maps of the elevation of a particular area, as a function of space. So usually those maps kind of look something like this, right? So you have different contours of elevation as a function of space. Right. And so oftentimes you want to find out. So if you were to take a path through this map here, right? So let's say that for some reason you want to walk that way, right? You want to find out, what's the rate of elevation change that you're going to experience walking along that path, right? And so we basically want to take the partial derivative of our function, but we don't want to take it in the x or y direction. We want to take it in this kind of arbitrary oblique direction. Okay, so we can do that, right? And the way we actually do that is we combine our gradient together with this idea of a dot product projection. So we can do this by projecting the gradient along that direction. Okay. All right, so in other words, we're going to take the dot product. So let's say that, this direction, we have it kind of quantified as some vector A, okay? So we can say that the directional derivative along the direction of A of our function f is equal to dot product of A and the gradient of f, okay? All right, so this symbol here, DAF, is directional derivative of f along a direction. Okay. Okay. But we want to make sure that when we take the dot product, we don't bias the gradient by any amount, right? So we don't scale it. So we want to make sure that our a vector here is a unit vector. Okay. And so just in case, right? Just in case our a vector here is not unit vector, we're also going to divide. Let me make this a bit cleaner. Okay, we're also going to divide by the original magnitude of a. Just to make sure, we don't include any additional bias. Okay. Okay, and so by doing so, we're effectively computing the partial derivative of f in that a direction. Okay? And we're doing so by taking the gradient and then taking the taking the dot product between the gradient and our vector. Okay. All right, any questions on this? Okay, so let's do a quick example just to kind of show how this is done. Okay, so let's say that we have a three-dimensional function here. So this is a function of a sphere, actually. So we have f of x, y, z is equal to 2x squared plus y squared, 3y squared, excuse me, plus z squared. Okay. We have some field quantity that changes as a function of x, y, and z. So this is a three-dimensional field. Okay. Okay, and so let's say that we want to compute the directional derivative along this direction. So our a vector here is going to be defined as 1, 0, minus 2. All right, and so with this is pretty straightforward. So we're just going to plug into the expression above, right? So first thing we need to do is we need to compute our gradient, okay? So we're going to take the gradient of f. We're just going to take partial derivatives of our function f here and then store it as a vector, okay? Luckily for us, this function here is very much, there's an x term, there's a y term, there's a z term, so make things very simple. So partial f, partial x here is going to be 4x. Partial f, partial y, that's going to be 6y. And then partial f, partial z is 2z. Okay. So this first term is partial f, partial x, partial f, partial y, partial f, partial z. All right. Next thing we need to do is let's go ahead and compute the magnitude of a, just so that make sure we have a unit vector. Okay. So magnitude of a is going to be equal to square root. We're just going to take the sum of the squares of each component of our vector. So it's going to be 1 squared plus 0 squared plus minus 2 squared. Okay. All right, so that gives us root 5. Right. So unfortunately, not a very convenient number, but sometimes that happens. All right, and so last thing we need to do is we just need to take our dot product. So we're going to take the dot product of a divided by a gradient or a magnitude multiplied by the gradient of f. Okay. All right, we go ahead and apply this. And so we're going to have a 1 multiplied by 4x plus 0 multiplied by 6y minus 2 multiplied by 2z. Okay. Everything divided by root 5. All right, so we just do the simple arithmetic here. We get 4x minus 4x minus 4z divided by root 5. All right, and that is our directional derivative for this fairly simple case. All right, any questions on how we got that result there? Okay, so one thing you should see from this is that our directional derivative and in fact our gradient as well, they change, right? So it's the derivative here is not a constant, right? So the magnitude and direction, I guess, of derivatives okay. Right, so you can plug in different values for x, y, and z, and you're going to get different gradient values, different rates of change depending on where you are, right? And that makes sense too, right? So if you go back to our example of the elevation plot, right? Right. So if you've ever been in any kind of mountainous region, you know that the elevation and the rate of change of the elevation is different depending on where you are. That's just how the natural kind of natural landscape kind of is. Right. So one thing that you might do sometimes, one thing you might see is that maybe we're interested in the rate of change at a very particular location. Okay. So that'll give us a specific number that we can do. Okay. Okay, so for example, let's evaluate our directional derivative. Let's evaluate our directional derivative at the point P is equal to 2, 1, 3. Okay. Right, so that's some location that we are going to evaluate at. Okay. So essentially, we're just going to plug in our values for x, y, and z based on that point. Okay. Okay. All right, so let's just go ahead and plug it in. So our value for x here is 2, our value for y here is 1, and value for z here is 3. Okay. So we go ahead and plug those in. We plug in 2 in here. We plug in 3 in there. Okay. All right. And so we do that, and we just kind of punch it into a calculator. We get rate of change of 1.789. Okay. So it's always interesting whenever you have a field. It's always interesting to see how your field changes or how its rate of change is in each given direction. Okay, but I would say it's equally as interesting, even more so interesting, to see which variables don't our rates of change depend on. Right. So if you look at our result here, right, we can see that the rate of change of our function in that particular direction does not depend on y. Okay, just because y is not in that expression at all, right? So that means if we evaluated this rate of change at a different location of y, right? So let's say we evaluated at p is equal to 2, comma, I don't know, 97, comma 3, okay? Right, so our X and Y values stay the same, but our Y is different. We're going to get the exact same result because our rate of change does not depend on Y, okay? So this is really fascinating because, when you're doing engineering analysis, a lot of times you're kind of asking yourself the question of like, we have this engineering quantity and we want to see what variables it depends on, right? If you get a variable, if you get a situation where your result or your field does not depend on a certain variable, that itself is a very interesting result. So, make sure that, when you're doing these kinds of problems, when you're doing these types of analysis, kind of pay attention to that because that often tells you a lot about a situation. And oftentimes can lead to a much simpler model if you don't need to be taking into account a certain variable. Okay. Yeah.
So for the in practice, since you're talking about the hiking, for example, does this mean that you're not essentially going in the Y direction?
So that means that, so this is an interesting case because, we're looking at the rate of change in a direction that does not include Y, right? So we're looking at a rate of change in the basically, in the X direction and a Z direction, right? So you're not really looking at the rate of change of Y. And our function here, has this kind of separation here. So that means that, if you're looking at the rate of change of this function in this particular direction, right? It doesn't depend on your Y coordinate, right? And so that means that, this is not a good example for height just because it's a three-dimensional function. And so, in reality, your height function would just be two-dimensional, right? But, let's say that we have a situation where, our height here, right? The rate of change does not depend on Y, right? And so that means that, all your rate of change is going to be in the X direction. So that in that case, you would just have a slope, right? So then your color contour plot would look just like something like this, right? Where, you can go any direction in Y, but your height is not changing. Which, when you look at something like this, it's really obvious when you see it. But, that's kind of the mathematical kind of. All right, any other questions on this? Okay. All right, so let's go over the next interesting application for the gradient, which is the direction of maximum increase. Okay. And then by extension, also the direction of maximum decrease as well. Okay. It's the same. Every uphill for someone is a downhill for someone else, right? Okay. All right, so recall, right? When we take the gradient of a scalar field, we end up with a vector field, right? Okay. And just like any vector, right? That means the gradient is also going to have a particular direction, right? Okay. And so the direction of that field actually has meaning, right? So at any given point, the gradients of our function points us in the direction of maximum increase or maximum decrease. It's a very simple concept that actually has, a lot of very kind of profound kind of applications and interpretations. Okay. Okay. All right. So let's see an example of this. And so for this example, we're not really going to do any numbers here. We're just going to kind of talk about it. Okay. So let's talk about heat transfer again. Okay. So if you are a mechanical engineer, you know that we have a heat transfer class, and so that is EGME 407. So that means for an entire semester you will learn heat transfer. But I will summarize the entire class for you in one statement here. Right? That's all you need to know about heat transfer. Okay? Heat energy will always do the same thing. So heat will always go from hot stuff to cold stuff. Okay. Wait a second. Yeah, no, that's it. That's the whole class. The whole class is all about just how heat goes from hot stuff to cold stuff, right? Right. More specifically, it takes the fastest path from the hot stuff, from the hottest stuff to the cold stuff. Okay. All right, and so that idea is actually encapsulated in the first formula you learn in the heat transfer class, known as Fourier's law. Okay? Right, so we are going to learn Fourier transforms later on, but this is it might be the same Fourier. I'm not sure. Right. Fourier, he contributed a lot to mathematics. He has a lot of stuff named after him, just like you were. Okay. Okay, so the first formula you learn in heat transfer is that Q, which is a vector. So Q here is the heat transfer rate. So you can see it's a vector quantity, so it has direction, is equal to minus K multiplied by the gradient of T. Where K here is a parameter known as the thermal conductivity. For our class, that's not really important, but I thought I would mention it. That just because I put a random letter there. Okay. But the most important thing here is our gradient variable. Okay. All right. And so if you look at our kind of our other interpretation of the gradient here, where the gradient points you in the direction of maximum increase or decrease, right? This will tell you that heat is always going to go in the direction of whichever takes you the fastest from the hot portion of your field to the cold portion of the field. Okay. Okay. All right. And so if we draw this out, right? So let's say that we have a two-dimensional domain here. All right, and so just to save myself some time, and I know not all of you have this available right now, so I apologize, but I'm going to use colors here to denote temperature. Okay. So let's say that we have a very hot corner up here, okay? Okay. And then the temperature kind of slowly kind of decreases from there. Okay, so we have kind of a warmer region here, okay? And then a cooler region here. Okay? Green. Okay. And then blue. Okay. Okay, so let's say our temperature field kind of looks like that, where the red is the hottest temperature that we have there, and the blue is the coldest one. Okay, so based on what we know, right, and so we don't even have to solve anything. We can already determine which way the heat's going to flow, right? We can say based on our Fourier's law and based on the fact that, we know heat's going to go in the direction of maximum decrease of temperature, okay? We know that heat, let me use pink for heat, okay? We know that heat's going to flow from the upper right corner to the lower left corner. Because it's going to flow in the direction of maximum decrease of temperature. There is more to heat transfer than this, but this, as long as you know this central idea, then you have a pretty good grasp of how most of heat transfer. But it's one of those things where the devil's in the details. But the overall idea of heat transfer is based on. Okay. So there's a similar thing in fluid mechanics as well. Right? So when you have a fluid flow that's bound on all sides, and so in other words, we have what's called internal flow. Okay. So a very common example of this is flow in a pipe, right? So we think about flow that's flowing in the pipes in your house or the pipes in this building, right? So fluid will always flow from high pressure to low pressure. So there is a very long, complicated formula in fluid. It's called the Navier-Stokes equations. There is a lot going on with that equation, but one part of that equation basically says that U is proportional to, where U is your fluid velocity minus the gradient of pressure. Now, you may not see it as the gradient of pressure in your fluid mechanics class. You may see it as the individual partial derivatives of pressure, right? But that relationship there tells us that fluid velocity and fluid mass is going to go from high pressure to low pressure. Okay. Okay. So let's say that we have kind of a complicated fluid flow situation here. So let's say we have a T junction. Okay. And let's say that we have fluid pressure monitors at each endpoint of the junction, right? So we know that the fluid pressure, let's say here is, let's say 90 PSI. Let's say here is going to be 30 PSI. Okay. Here, let's say, well, it'll be 120 PSI. And then over here, let's say we'll be at atmospheric pressure, say 0 PSI. Okay, and you want to determine, which direction the fluid is going to go, in this kind of situation here. Okay. Okay. All right. So if we look at each kind of outlet individually, right? So we look at each kind of portion here, we can say whether flow is going to be going into that portion or out. Okay. Now the most obvious one here is going to be the extremes, right? So we know from the 120 PSI one, that's the highest pressure we have in the system. We know that that's always going to be providing flow to all the other outlets over here. Okay. Right. Because fluid's going to go from that highest pressure to the most. And then same thing for the other extreme, the 0 PSI. We know that fluid is always going to want to go in that direction because that's the lowest pressure in the system. Right, so we can say unequivocally that the bottom junction there, the 120 PSI, that's going to be an inlet. That's where flow is going to come in. And the 0 PSI, that's going to be an outlet because that's the lowest pressure. Flow is always going to come out there. Right. Now for the other two, it's a little bit interesting, right? And so you may see this and think, okay, 90 is greater than 30. And so you might have flow that's coming that way, right? And then 30 is also greater than 0, so flow should be going that way as well. Now, for those ones, it's a little bit more complicated because the flow from the 120 psi, that's also going to be pushing the fluid back that way to here. Right? And so, for those ones, it's the situation is probably a bit more complicated. You might have some recirculating flow, you might have flow that's stagnating, you might have some turbulent flow going on there, but at least you have kind of a general sense of kind of what's going on in this situation. All right. Any questions on this? Okay. One more example, just because this is kind of a cool application here. There's so many applications for this the direction of maximum increase. Okay. Okay. So another way you can look at the gradient if you have a contour plot. So if you're not familiar, a contour plot is kind of a visual representation of a field quantity. Right? So we've already kind of seen it a little bit, right? So this kind of beautiful art thing that I drew of our temperature field, this is technically a contour plot. This image I have here of our elevation, this is also a contour plot. Okay. So contours are a very common way to display field quantities. Okay. Right. And so the way to read the contour plot, and so sometimes it's as easy as just kind of interpreting the colors. Okay. But you may see black and white contour plots. So these are less common nowadays, but you might still see them. Okay. And so the idea with the contour plot is that you have some quantity, some field quantity that's going to be varying in space. Okay. Right. So we have some function x and y. And so let's say that we have some contours that look like this. Okay. Okay, so the way to interpret this contour plot is that every line that you see there is a line of constant f. Okay. Okay, so we can say each contour line represents a path or represents a part where the value of our function remains constant. Okay. And sometimes you'll see this too. And so if you look at some like old school kind of topology maps of a certain region that shows you elevation, right? If you look at these color contour maps, you'll see that next to these lines, you'll see things like height is equal to, I don't know, 400 meters or something like that. Okay. So that means everywhere along that line, the height of maybe above sea level is going to be a constant amount of like 400 meters. Okay. And maybe the next contour line will say height is equal to maybe 375 meters. Okay. Next line is h is equal to 350 meters. Okay. Okay. Right, so there's always going to be regions, or so there's always going to be paths where your function value is going to have the same value. Okay, so that's how you read the contours. Now, what's interesting is that when you take the gradient, okay, we know by now that taking the gradient gives us a vector, right? So the gradient is always going to point you in a direction that is perpendicular to the contour lines. Okay. All right, so if we were to compute the gradient of f here, right, it's going to produce vector field, right? Right. And so if you evaluate those vector fields on those contour lines, you'll see that the direction that's given to us is always going to be perpendicular to those contour lines. So that means if you're standing on a particular contour line, well, technically, you're always on some contour, right? The gradient will point you in a direction of maximum increase from that contour or maximum decrease. Okay? The way I always like to think of this is that, let's say that you're on some kind of mountainous path right there, and some, I don't know, magical reason you knew the gradient of the topology of wherever you're standing, right? If you had a marble, right, you would then know the exact direction to which to roll the marble that would result in the maximum speed. Okay. It's a very theoretical situation. You're never going to find yourself in that situation, but think of it. That's how I like to kind of think about these things. Yeah, exactly. Yeah, like rolling a rock down, throwing a rock down. That's kind of what these things are. Okay. All right. Any questions on this? Okay. All right. So for the last 20 minutes of class today, let's talk about the next derivative operation, which is the divergence. Okay. Now divergence is interesting, right? So if you notice that, when we did our gradient operation, we only did it on a scalar field, okay? Because, you can think of the gradient as kind of stepping up in dimension where, you start with a scalar field, you take the gradient, you end up with the vector field, right? So you kind of go up from a scalar to a vector, right? We didn't talk about it here, but you can also take the gradient of a vector field, and by doing so, you end up with a matrix, okay? So it's a way to kind of go up in dimension. Divergence is kind of the opposite. Okay? So you can only take the divergence of a vector field. There is no such thing as the divergence of a scalar field, and you'll see why very quickly. Okay. Right? Because what happens when you take the divergence of a vector field is that you actually end up with a scalar field, right? So the divergence actually steps down. Nope. Okay. All right. So the way you take the divergence is actually kind of a combination of a lot of operators that we've looked at already. So we are going to use the nabla. So basically every operation today, we're going to use the nabla. And then we're actually going to take the dot product of between the nabla and our vector field of interest. Okay, so we're going to take nabla dot product with V. Okay. So if you kind of break this down and you kind of look and see what these kind of vectors look like. So the nabla, it's technically not a vector, but sometimes it's useful to think of it as a vector. It's a vector that contains all the partial derivatives. All right, so this is going to be partial x, partial y, and partial z. Right? So you think of it like that. And our vector v here, so v here is just going to be a generic vector field. And so this is going to have components vx, vy, and vz. Okay. So if you think about it like that, then taking the divergence ends up really easy to do because we're just going to take the dot product between these two vectors here. All right, so we end up with partial Vx, partial x, plus partial Vy, partial y, plus partial Vz, partial z. Okay. So divergence, very straightforward to compute, right? So as long as you have your vector field, you know each of its components. And so you're just going to take the partial derivative of each component in the direction that matches that component, right? So you take the x derivative of the x component, the y derivative of the y component, the z derivative of the z component. You just add it all together and you end up with divergence, okay? Okay. Now, divergence, I would say, probably less applications that we can kind of really talk about here compared to gradient. Gradient has a lot of really interesting applications. But where you'll see the divergence operator a lot is actually in the area of fluid mechanics. Okay. Specifically, you'll see the divergence used whenever we are considering conservation of mass. Okay, so just a couple of examples. So we have different conservation of mass equations for an incompressible fluid and a compressible fluid. Okay, so first let's go over the incompressible fluid. Right, so an incompressible fluid is basically a fluid where the density is relatively constant. So you're talking like most liquids, right? Um, incompressible really means incompressible, right? So if you have like a water balloon or a balloon of water, right, you can kind of squeeze it, right? And you can kind of change its shape, but you cannot change the amount of fluid or volume that it's taking. Right? So incompressible fluid usually means some kind of liquid. And honestly, most gases are like that too. Okay. So the formula for conservation of mass here is very simple. So you're going to take the divergence of the vector field, of the velocity field, excuse me. Okay. And then what you're going to say is that the divergence of the velocity field for an incompressible fluid is equal to 0. Okay. So if your fluid is mass conserving, then it should satisfy this equation. Okay. Actually, let me rephrase that. All fluids are mass conserving. We can never violate conservation of mass. We can't create mass out of nowhere. We can't destroy mass. And so, every fluid will satisfy this equation here. Okay. The other one, okay. The other expression for conservation of mass that, for the most part, I think most fluid courses will not go over just because it's more complicated, is one for a compressible fluid. So the idea with the compressible fluid is one where you can kind of essentially kind of squeeze it enough or provide enough pressure such that the volume of the fluid actually changes. Okay. So physically what's happening for a compressible fluid is that, you can basically squeeze it enough such that the molecules actually get closer together so that the fluid actually takes up less space. Okay. Okay. And so in these situations, the density is variable. And so we have partial rho, which is the density, partial T plus divergence of the density multiplied by the velocity. Okay. Now, these equations, obviously I can't, this is not a fluid mechanics class, so I'm not going to test you on this, but I'm just kind of showing you some examples where the divergence kind of plays a role. Okay. Okay. But I think what's more relevant for everyone here is to talk about, what does the divergence actually tell us? Oops. Right. So if you're taking the divergence of a vector field, what are you really doing, right? So what information are we really kind of looking for in that divergence? Okay. So when you take the divergence of a vector field, you're essentially asking you're asking the vector field, how much are you expanding in given directions? Okay. Now, I think the best way to kind of illustrate this is to, once again, I apologize because fluids is in my background, so I think of everything in terms of fluids. But let's look at the divergence of a velocity field, right? Okay. So we take the divergence of a velocity field. We're just going to look at two dimensions, just to keep it simple. So in two dimensions, the divergence of the velocity field is we're going to take the partial derivative of the x component of velocity, u, plus the partial derivative of the y component of velocity, v, and then add them together. Okay. Okay. So let's look at a situation where, one of these terms is positive and the other term is negative. Okay. Okay, so let's say that the partial derivative of u with respect to x is positive, and the partial derivative of v with respect to y is negative. Okay, because we know, right? We know from above here that for a mass-conserving fluid, the divergence of the velocity field must be 0. Okay. All right, and so if one of these quantities is positive and the other is negative, that kind of implies the fact that, these two quantities are going to essentially balance each other out. So essentially, one direction of the velocity is speeding up, the other is slowing down. Okay. Now this situation happens a lot, right? And so, I think the most common situation of this is flow through a nozzle, right? Right. So let's say that we have a converging nozzle like this. Okay. So you see this in your hose, right? And so you basically constrict the flow to force the flow to have a higher velocity. Okay. Okay. So what's going to happen here is that flow is coming in. It's forced to bounce off the walls of the nozzle, okay, and then converge. And then as the flow converges, the flow is going to speed up. Right? That's just conservation of mass. You're going to stuff everything in there. Then the flow has to kind of speed up to kind of maintain that mass flow. Okay. And so in this sense, you can see that, as we travel in the x direction, right, where the x direction is, this direction here, right? Right. What's happening to the horizontal velocity as we move in that direction? It's increasing, right? So we can say that partial u, partial x is going to be greater than 0 because we have a flow that's essentially kind of speeding up. Okay. Now to balance it, right? To balance it, that means our partial v partial y has to be negative. Okay? Okay. So in other words, the y velocity, must have its value be decreasing with that increasing values of y. And that's the case here because we can see that the flow is essentially converging here, right? So eventually we're going to reach a point where the y velocity here is going to, start, it's going to start with some value and then it's going to slow down, right? Once it kind of reaches the center here. And so it makes sense that our y velocity there is essentially slowing down because, the flow is kind of converging through that. Right? Right. And so, in some sense, you can say that the speed up in the x direction is compensated by the slowdown in the y direction. Right. That's essentially what the divergence kind of tells us. Right. And so if one velocity is expanding, that means the other velocity must be kind of contracting. Right? That's kind of how we usually describe it in fluid mechanics. Okay. Okay. But you can also look at a situation where this is not true. Right. So what if we have a situation where both are increasing, right? So we have partial u partial x is increasing and partial v partial y is also increasing. Okay. Right. So basically the flow velocities in both the directions are actually speeding up. Okay. So that can happen, right? So because of conservation of mass, we know that these two quantities must equal, or when you add them together, they must equal 0. Okay. And so you have a situation where both the x direction and both the x velocity in the x direction and the y velocity in the y direction are increasing, right? We essentially have a flow that looks like this, right? So we have a flow as we go in this direction, the u velocity is increasing. Okay. Then as we go in this direction, the v is also increasing. Okay. So you kind of have a contradiction here where, we have fluid velocity keeps increasing as you keep going along, right? But in order to keep increasing velocity, that means we have to kind of add mass into the system. And right, and the main tenet of conservation of mass is that we cannot create mass from nowhere. And so, we cannot create mass to sustain the situation where we're increasing the velocity in the x and y direction at the same time. And so that situation obviously violates conservation of mass, and therefore we cannot have that situation. Okay, so that's essentially what the divergence tells us. So the divergence will tell us is it's a measure of how our vector fields are expanding in each of the given directions. Okay. Now, for fluid mechanics, the divergence must equal 0. But, there are situations where you do see some expansion in certain other vector fields, mostly in electrodynamics. That I can't comment on too much, though, because, I don't have that much of background, but I do know that is okay. All right, any questions on any of this before we wrap it up for today? Okay, all right. So next time I see you guys will be on Tuesday for the midterm exam. So please make sure you are here for that. Remember, you can bring a pencil, bring a calculator. Please bring your cheat sheet as well. And then when we come back to class on Thursday, we'll pick this up and talk about the curl. Right. So thank you guys for coming today. Hope you guys have a good rest of your day. Best of luck studying over the weekend, and I will see you guys next week.
Question.
Yeah.
I need to OD, so obviously links to study postures. Any just topical questions, like conceptual things you want us to focus on?
So it's all the study guide. So yeah, so that's look at it. So the first section of the study guide is conceptual concepts. Something cool.
Okay, cool. So, okay, that's on the model.
It is, I think I might have emailed it, but it's also on the page for this week. So if you look under week 7, there is a PDF there that says midterm goals.
Okay.
Yeah.
Thank you.
Yep.
With cheat sheet, get it in front of it.
Yep. Front of it. You can write it or type it too, whatever you. Yeah.